about non-invertible symmetries and protected topological spaces and duality viewpoint.
Yeah, thanks for Ifan to invite me here and give the talk. I'm Weiguang. I'm a postdoc at University of Southern Denmark, and this work is collaborated with Lin Hao, who is a postdoc at University of Ghent, and Masahiro Yamazaki, who is a professor in University of Tokyo. So today, my topic is about non-invertible symmetry. And specifically, we are interested in gapped phase of matters with one ground state, which is the symmetry-protected phases. And we are using the method called Farmer-Wanius duality, or in other words, just gauging the discrete symmetries. So I mainly discuss this in a lattice perspective. So I will try to be kind of precise. I will just introduce you to some lattice models with non-invertible symmetries in the beginnings. But to begin with, if you have any questions, please just stop me and ask me. And before, what is a symmetry? Why symmetry is important? A symmetry in the nature is a pattern that is invariant under certain manipulations like reflection, rotation, or translations. And in the physics system, it is transformations that leaves the Lagrangian or the actions invariant. In the quantum sense, it means that we have an operator that commutes with Hamiltonians. Because they are commutes, so we can kind of diagonalize them simultaneously, and the symmetry will give us some degeneracies of the spectrums. So here gives us some modern perspective of our ordinary symmetries. So we use codimension 1 topological operators with group multiplication law to describe our symmetries. So what is codimension 1? So in a D+1 dimensional system, the symmetry operators act on the whole spatial slice, which is D-dimensional, and which is codimension 1. Topological means that it commutes with a Hamiltonian so that you can move it in the time direction freely. And the group multiplication law means that the symmetry, the fusions of symmetries described by groups, like the Rubik's Cube, you can always have identity operators, leave it invariant, or you can compose two different symmetry transformations to make a new one. And for every symmetry operator, you can always find the inverse. And now in the with this modern language, we can kind of generalize the idea of symmetries by relaxing each conditions. For example, if you relax the codimension 1 conditions, now the symmetry operators can act on some higher codimension surfaces, which gives you the higher form symmetries. And if you have mixings between different forms, you can have so-called higher group symmetries. And if you also certainly relax the topologicalness conditions on the space, you can have so-called subsystem symmetries. So this is the one kind of generalizations of the ordinary symmetries. And the second one is to relax the group conditions. You can have more general fusion rules like fusion categories. And this is so-called non-invertible or categorical symmetries. And to imagine it from the Rubik's Cube's examples, so the action of the symmetry, non-invertible symmetry operator on the states is like you put a fire on this Rubik's Cube, so it cannot go back to its original states. And I will show you that it really like you act some projection operators on your states, so you can never go back. So this is the ideas of how we generalize the symmetries. And what is the symmetry beyond group structure? What is kind of data? So in 1+1b, the non-invertible symmetry is described by fusion categories. The data of the fusion categories includes its object and fusion algebras. So you can have two different non-invertible symmetry lines, and it will fuse into the direct sum of other symmetry lines. And for three kind of fusion of symmetry lines, you can have different ways to fuse them, and they are related by the second data called F symbols. And if you fuse 4 of them by using the F symbols to go two different fusion, you can get the same result. And this Pentagon equations give you the constraints of your F symbol data. And together, these two data describe fusion categories and also describe your non-invertible symmetries. But in my talk, I will kind of only focus on this object and fusion algebras. And what are the non-invertible symmetries I'm interested in my talk? So there are mainly two kind of categories and two sets that I'm interested. So for any abelian group, you can just add one single non-invertible operators to form a so-called Tambara-Yamagami fusion categories. So the fusions of the non-invertible operators give you sum over the all the group elements in your abelian group. And the fusions of the abelian element with the non-invertible one gives only the non-invertible ones. So on the lattice, the simplest model is a critical IC models with the abelian group to be Z2. And on the lattice, the Z2 is realized by spin flip, and the non-invertible one is realized by the Kramers-Waniers. I will discuss these models in detail in the next page. And for any non-abelian group G, there is a associated representation fusion categories, where the objects are the irreducible representations of the non-abelian group G. Because it is non-abelian, it has irreducible representations with higher dimensions, which give, and the fusions is a tensor product of these irreducible representations. And the fusions of the higher dimensional irreducible representations will generally give you the non-invertible fusion groups. So on the lattice, the simplest example is the cluster states, where the non-abelian group is D8, and the fusion category is rep D8. So the rep D8, so the D8 group has 4 one-dimensional irreducible representations from the Z2 times Z2 group, and realized by spin flip on the even and odd sides. And it has 1 two-dimensional irreducible representations, which is a non-invertible object, which is realized by the product of Kramers-Waniers of the even and odd side feathers. And this model is described in Southen and Southen's papers recently. So these are the two set of fusion categories that I'm interested in, but there are a lot of more that I didn't include in my talk.
Is it understood how to go from this cluster model to a model that has rep H8 symmetry now? I mean, since then?
I think for the cluster models, it has both rep D8 and rep H8.
It has both, okay.
And the operators between rep D8 and rep H8, the difference is one-side lattice translations.
It's a lattice translation.
Yeah.
But in the continuum, that's well, in the continuum, sometimes it's given by the Churchill equation.
Yeah, I think Ichiro told me that it's swapping the Z2.
But the IC square will be swapping the Z2.
Yeah.
But you say on this, but it's lattice is realized by translation.
Yeah, it's a one-side lattice translations. So now I will show you the simplest case of non-invertible symmetries. So the non-invertible symmetries can be found in the phase transitions. So our setup is a closed spin chain with L sides, and on each side there is a spin up and down, and we can act sigma z and sigma x on each side. So here is a quantum IC models with a parameter g. So the first term is product of sigma z's. On the adjacent side is try to align your spins in the z directions. And the second term is a sigma x, is try to align your spins in the x directions. So this Hamiltonian has a Z2 spin flip symmetry, which is the product of sigma x on every side. And it commutes with the Hamiltonians. When you tune the parameter g, so the two terms compete and you can have a phase diagram. When g is very small, the first term dominates and you are in the Z2 symmetry breaking phase, and the ground state degeneracy is 2. It's spanned by the all spin up and all spin down. And when G is very large, you are in the Z2 symmetric phase. Now you only have one ground state, which is the spin in the x directions. And in the middle, in the G equals to 1 point, there is a second order phase transition, which flows to the critical icing CFT. So now there is duality transformations, so-called Kramers-Waniers, that maps from one phase to the other. So it it just do the same. It exchange the first term with the second term. So the D is an operator that implements this duality transformations. And because of these properties, it maps the Hamiltonians with coupling G to the Hamiltonians with coupling G inverse. And the Kramer-Weiguang is also understood as gauging this Z2 spin flip symmetries. And then I will show that it's kind of, because we are on a finite dimensional Hilbert space, every operator is just a matrix. I will show that this Kramer-Weiguang is a matrices that is not invertible. First, let's look at the transformations on the states. Of course, it maps the spontaneous symmetry breaking phase to the symmetric phase. It maps the all spin up and all spin down to this trivial phase, which lives in the V2 symmetric phase. And by doing some algebraic, you can define the linear combinations of these two states, which is annihilated by the operator D. So this means that this operator has a kernel and it is non-invertible. You cannot find an inverse for that. So this Kramer-Weiguang duality operators is non-invertible. And at the critical point, this D commutes with the Hamiltonians. And therefore, we find it becomes a symmetry at the critical point. So the bonus here is that the KW duality becomes a non-invertible symmetries at the critical point. And this is the first, maybe the simplest examples of non-invertible symmetries on the lattice. And we can further write down some explicit formulations of the Kramer-Weiguang duality operators. I will not say the details here, but you can check that the fusion rules equals to the 1 plus U, which gives you the kind of Tamara-Yamagami fusion categories. And nowadays there's a multi interpretations of this Kramer-Weiguang duality operator that I comment here. So back in last century, from Kramers and Weiguang, they designed these dualities to map classical models with Z2 symmetries from the high temperature to low temperatures. Therefore, they can find the phase transition point. And recently, it is realized by these peoples of some topological defect lines separating the classical models. And in the quantum sense, it is a duality between quantum spin models with Z2 symmetries that I showed you. And it is realized by gauging Z2 symmetries. And further, it becomes a non-invertible symmetry at the critical lines. And people also show that the non-invertible operators on the lattice can be built from a sequential quantum circuit way. And it can be also understood as compositions of quantum operations, including measurement. For example, you want to act the non-invertible operators on an operator localized here. You first add a sinus qubit here, and you can have a fusion of two non-invertible operators. You kind of do some local unitaries to move them apart. And then you act operator O, and then you move them together. And finally, you do a measurement. Then you get the actions of non-invertible operators. And all the steps can be realized in quantum channels. And in the last, it can be realized in the MPO representations. And there are maybe other interpretations. And this is some kind of modern understanding of these Kramer-Weiguang dualities. And next, I will introduce you the second example of non-invertible symmetries that also come from the Kramer-Weiguang dualities. So the claim is that the Kramer-Weiguang dualities maps the theories with symmetry D8 to the symmetry with rep D8. First, the model with the symmetry D8, I just gave an example here is a XXZ models, where, so here the model have a larger symmetries. It has a spin rotation symmetry between the X and Y directions, which is U1, and also a Z2 spin flip symmetries. And the D8 is a kind of subgroup of these O2 symmetries. And by doing the Kramer-Weiguang transformations, you just do the duality transformation directly, you can get the so-called Ising zigzag models. So here, I will first show you the lattice realizations of the D8, which is a spin flip, which is a Z2, and the spin rotation, which is a Z4. And on the left side, we have 5 elements of the rep D8. 4 of them are Z2 times Z2, are realized by the spin flip on the even and odd side. And the last one is a non-invertible operators. It is realized by the so-called sandwich constructions. So how to understand this? Some technique. Okay. To understand this, so we have non-invertible duality transformations maps from theory A to theory B. Here is these 2 models. And in theory B, there is invertible lines we label by eta, which is the Z4 lines. Then you can use 2 kind of non-invertible. You can use D and D dagger to go from A to B back to A's. And if you shrink the size of B, you can get a non-invertible fusion, non-invertible lines purely in theory A. And this just gives you the non-invertible lines in the rep D8 theory, which comes from the Z4 lines in the D8 ones with the non-invertible duality operators. So this is a way to construct non-invertible symmetries from the one with the invertible one symmetries and the non-invertible duality transformations.
This is just because D is the interface for the Z2 gauging.
Yeah, yes, that's true. And in general, if you have a non-abelian group, and you can gauge the non-normal subgroup, which can give you a non-invertible symmetry. And this is a main kind of method I use here in my talk. So how to find non-invertible symmetries in lattice models? So one sentence, maybe you just find a non-invertible operators that commutes with the Hamiltonians. But I just be loose here. So there are non-invertible operators like projection operators, but I don't include them as an interesting non-invertible operator.
But what's your condition on the operators that make it interesting for you to search for them?
Well,
so what additional condition do you want to put on this operator apart from commuting with the Hamiltonian?
Well, I mean, maybe I just think it cannot be written as a sum of other symmetry operators. Maybe in the field theory, it seems like it is simple in that.
In the field theory, there's a very simple way to isolate the kind of symmetry defects that we think are interesting. But on a lattice, what will be the reasonable criteria?
Well, I do not know a general criteria, but I have the following kind of 2 ways to find it. So first, there is a non-invertible duality transformations that I showed you, like Farmer-Wannian dualities, and it will become a non-invertible symmetry at the self-due point. So in 1+1D, it includes some generalized Farmer-Wannian dualities, like gauging ZNs. And in 3+1D, you can gauge the one-form symmetries. This will give you the Wigner dualities. So the first way is generally finding some Tambara-Yamagami fusion categories. And in the second way is just if a non-invertible duality transformations map a theory A, which possibly with a group symmetry to a theory B. So we can construct the non-invertible symmetry in theory B via the sandwich construction I showed you before. So this is the rep D8 symmetry in 1+1D. Also in the example in the last page. So in theory B, we have a general U1 semi-product Z2 symmetries. And if you consider the whole symmetry and gauge the Z2, you will get a cosine symmetries, which the fusion rules follows by the cosine product. And this generally gives you some representation fusion categories. So I kind of mainly use these 2 ways. Yeah. And there are also exist other constructions like anion chains for more general fusion, non-invertible symmetry like Fibonacci fusion categories, but I will not study them here. Yeah, please.
Yes, maybe one additional thing that you might impose to make them interesting is that, like, in the continuum, if you have a line, you can not only orient it parallel to space, but you can orient it parallel to time.
Yeah, you
And
can
then instead of having an operator on the Hilbert space, you can twist the Hilbert space by the line.
Yeah.
So do you have a notion of inserting a point-like topological impurity on the lattice that corresponds to these operators? Or...
Yeah, yes. I think you should, when we discuss non-invertible symmetry, you should always can define a defect Hamiltonians, which is the twist of the non-invertible operators. It kind of shows some localityness of the non-invertible operator. Yeah. For every symmetry I discussed here, we can always define such defect Hamiltonians. Yeah. And we can use some unitary transformation, local unitary transformations to move the defect so that it is topological. Yeah. Yeah, thank you for the questions. So I kind of introduce you the non-invertible symmetries on the lattice and why they are important. So even for ordinary symmetries, they are important in several different ways. First, continuous symmetries means conservations, which is given by the Noether theorem. And for generalized symmetries, we have similar things like flux conservations in free Maxwells. It is given from the one-form U1 symmetries. And also symmetries classify different phases according to Landau's. So we can either have symmetry preserve, or we can have phases preserving the symmetry, or the phases spontaneously breaking the symmetries. And for example, some topological orders in 2 + 1D, like torical, can be understood from this perspective, like it is a symmetry breaking phase of the one-form Li2 symmetry. And also symmetry can constrain your low energy dynamics from the so-called 'to Hooft anomalies. So if a model has a symmetry with 'to Hooft anomaly, the model cannot be trivially gauged. It means that the model can either, if you do the symmetric deformations, the model will either flow to a gapped phase with some degeneracies on the ground state, or flow to a gapless phase. So it prohibits the case that the phase is trivially gapped. So these are all the importance of why we study symmetries. And here I give you some landscape of generalized symmetries. Starting from ordinary symmetries, you can do several different ways of generalizations, and you can combine different generalizations. And each new symmetries can give you kind of new physical applications. For example, the subsystem symmetries gives us new phases called fracton phases, where the quasi-particles have mobility constraints. It cannot move, or it can move only in some dipole. And higher form symmetries gives us some order parameters for studying the phase transitions with confinement. And all the generalized symmetries will give us spectrum degeneracies, selection rules, constraints on your renormalization group flow, and constraints on your low energy EFTs. And today I'm looking at this kind of perspective. I'm introducing you to some non-invertible symmetries, and I will use these symmetries to study some new phase of matters. So this is kind of the aim of my talk. If no further questions, I will just go. So Landau tells us that phases represent symmetries. So if you have symmetries, you can have new phases. And in recent years, we also found many exotic phase of matters that beyond Landau's descriptions. For example, like the topological insulators. And to show it, to show the phase of matters beyond Landau's paradigm, I will give you examples that in 1 + 1D with a given symmetry G. So Landau tells us that there are phases spontaneously breaking symmetry G, or phases preserving the symmetry G. But in phases preserving the symmetry G, there can be further classifications. So there can be trivial phase, or there can be some non-trivial phase that cannot be connected to the trivial phase. If you consider the symmetry, these phases are different. If you allow some deformations that break into symmetries, they belong to the same phase. So therefore, we kind of call them phase that symmetry-protected topological phases. So this is the one I'm interested in this talk. And some application is that many topological insulators are protected by U1 particle number conservations and time reversal symmetries. So I will further give you the examples. So SPT phases in 1+1D. So it is a gapped short-range entanglement phase with certain symmetry G. On the closed chain, it is uniquely gapped, where on the open chain, it has edge modes at the boundaries. So here is a kind of cartoon. So we have unit cell with two spins, and between unit cells, there's some short-range entanglement. But if we put it on the open chain, we cut it, and there are some dangling states on the boundaries. This gives you the edge modes. And the edge modes are characterized by projective representations of your symmetry operators as your boundaries. So the simplest example is a Z2 times Z2 SPT, where the Z2 times Z2 given by the spin flip on the even and odd side. So here are two SPTs. One is a trivial phase, and the other one is a non-trivial phase, which is given by the sigma Z times sigma X times sigma Z. So how to distinguish these two phases? So we just use the property that there are some edge modes if we put the two phases on the closed chain. So they have some interface, and we are going to find some edge modes or projective representations at the interface. So we will study the ground state, and we will add these two Z2s on the ground state. So for example, in this system, the two Z2s commute with each other. But if you act on the ground state, you need to consider of some constraints. And by imposing these constraints, these two symmetry operators can be simplified. So they factorize around the boundaries. And at each boundaries, you find that they didn't commute with each other. Therefore, on the boundaries, the boundary state must form a projective representations. So this is a way to detect different SPTs. And I will also use this method later in the SPTs with non-invertible symmetries. So SPTs with group symmetries in general dimensions, there are several perspectives. In the field theory, GSPT is an invertible topological quantum field theory with some anomaly inflow to the boundaries. And in the lattice, the GSPT phase is a gapped phase with unique ground state with symmetry G on the closed manifold. With open boundary conditions, there exists anomalous edge modes on the boundaries. And in the mass perspective, the GSPT in the D+1 dimensions, or the anomalies of G symmetries on the boundary in the D dimension, is classified by the group cohomology like this. So we want to kind of ask the same questions for the SPTs with non-invertible symmetries. How do we classify them? So this work is pioneered in Yifan and Ran's work. They studied in the field theory perspective. And then later, there are works followed in the lattice. So in the first work, people are studying some group-based cluster state. So on the lattice, they do not consider Z2 spin, but some general group labeled spin. And in the second case, Southen and Southen study the case of SPT with RAP-D8 symmetries. They classify them. There are three distinct RAP-D8 SPT, and they construct corresponding lattice models. And in the third paper, Kensei studies the SPT with non-invertible symmetry in the metric product state setup. And later, there are many more papers I didn't cite. And in the math, because we are now dealing with a fusion category rather than a group, so the SPTs is corresponding to the fiber functors of the fusion categories. And in this work, we are trying to use duality or gauging method to study SPTs with non-invertible symmetries, where the non-invertible symmetry is due to a group symmetry. And so the whole picture is like this. There are some duality transformations between a symmetry C1 and the symmetry C2. For example, the rep D8 and D8. And then the duality is gauging the two symmetries. Actually, you can just understand the whole pictures in these examples. And on the lattice, the gauging Z2 is just perform the primary winding transformations directly. And because of the duality transformations, the gap faces on each side are one-to-one mapped. For example, the SPT faces with symmetry C1 are corresponding to some SSB phase in symmetry with symmetry C2. And therefore, just find what kind of SSB patterns corresponding to the SPT. And classifying these SSB patterns, we can do the classifications with the non-invertible symmetries. Yes, we are mainly gauging the non-normal Z2 subgroup as the duality transformations. And in 1+1D, we are interested in rep D2N, which is due from the D2N symmetry. And I will illustrate this method using the examples of rep D8. So here is
I'm missing some keyword, but what does it mean that gauging is a duality? Because I mean, you have a group. If you have a global symmetry, you gauge it, you get a different.
Yeah. Here we just generally get a different models. So I call it duality because usually in the literatures, people call these discrete gaugings like, for example, gauging Z2 is like Palmer-Wanian dualities. But
it doesn't come at one. I mean, a duality means that these two models are the same model with different names. While when you gauge a symmetry, you get a generically. I mean,
sure.
The gluons and you don't have the same model as QCD, right? So
sure. So the precise way is just saying it is just gauging the discrete symmetries. Yeah.
It's indeed a confusing terminology, especially in the community, because these two notions agree in the Kramers-Schweiner case. So it happens in the Kramers-Schweiner case for the isotope chain.
Yeah.
The duality there is equivalent to Z2 gauging. And then they extrapolate from there to the notion of duality being equivalent to discrete gauging. But that's not what typically we think about.
Yes.
And in this case, they may be different, these two models.
Yeah, they're different.
The two models are different with different symmetries. Yeah, that's a correct.
But for the discrete case, I think what we want to try to say is that it's dual in the sense that you can reverse it. You can undo the gauging, unlike what we do in continuous gauge theory.
Yeah.
I would even say in the case of the ordinary Kramers-Wanian duality, it's probably abusive to call it a duality because it maps the spontaneous symmetry breaking phase to the symmetry preserving phase. So it doesn't, I mean, these two models aren't the same. They have different number of ground states, for example. So, I mean, when you're at the critical point, it is a duality, but away from the critical point, they still call it Kramers-Wanian duality. That's maybe more properly.
If you add to the topological sector.
Yeah, the topological sector.
Yeah, so it's kind of this point of view is explained in detail in the paper that Lati Seiberg wrote with Anton Kapustin.
I see. Yeah. Okay.
Yeah, including Kramers-Wanian and also Wagner duality.
So this field, every word is a misnomer, like theft anomaly, etc.
Yeah, for sure. Yeah, that's total anomaly matching.
The duality is such an overloaded word by now. It appears in like 20 different contexts.
Anomaly is similar.
We should embargo the word duality for now.
Yeah, that's why I kind of emphasize it's just the gauging of discrete symmetries. You just understand it this way. And duality is just a name or a not improper name. Yeah. Sorry about that. So here is a general picture. We have the general method is we have duality transformations. We have discrete gaugings from theory with symmetry C1 to symmetry with theory with symmetry C2. And the gap phases of symmetry C1 and of that of symmetry C2 are one-to-one correspondence. For example, if we just use a KW, which is just exactly this mappings, and C1 and C2 are Z2. So in 1+1D, there are only two phases. One is a symmetric phase, one is an SSB phase. and they are kind of one-to-one mapping under the KW transformations. So therefore, the classifications and the constructions of the gapped faces with C2 symmetry, which is usually a group symmetry, implies the classifications of constructions of the gapped faces with C1 symmetry, which is maybe probably a non-invertible symmetry, and in particular the C1 SPT faces. Here I will use the RAP-D8 models to illustrate the general method. So here I'm just focusing the KW transformations. And on the right-hand side, we have a group, which is D8. On the left-hand side, we have a category, which is a RAP-D8. So the D8, I just list all these elements here. So for a symmetry with C1, the non-invertible symmetry with a Z2 subsymmetry, we gauge the Z2, and we can, for C1 SPT, we gauge the Z2, we can get the faces with symmetry C2, but the Z2 is spontaneously symmetry breaking. So for example, the RAP-D8 SPT face is due to the D8 faces that spontaneously breaking the Z2, which is where the Z2 is generated by U. Then we just need to find the unbroken symmetry patterns for the face on the right-hand side. So what kind of unbroken symmetry can you have? So it's just the kind of group questions. You just need to find the group subgroup of D8 with order 4 without the U element. The first case is, yes, so the classification of SPT faces with symmetry C1 corresponding to the classifications of the unbroken part of C2. So the first one is that you just, this Z4 is unbroken, like this. The second case is that there is a diagonal subgroup, a diagonal group of this Z4 and Z2 is unbroken. Actually, you can only find these two cases. So these are the two cases of unbroken symmetry of the right-hand side. Then you can kind of stack the unbroken symmetry SPT to the face, and which do not change your SSB patterns. And the SPT of the unbroken symmetry is just classified by the ordinary group case, by the group cohomology. Like for the first case, it gives you the Z1 classification, meaning that there are only one faces. And for the second case, there is a Z2 classifications, meaning that there are two faces. Therefore, by using the dualities, we can see that the classification of RAP-D8 SPTs are given by Z1 direct sum Z2. And this kind of reproduce the mathematical result also in the Southen's papers. And we can do it for general case, for example, the RAP-D2N. This method holds generally if the group symmetry C2 contains a zero form.
Can you go back one slide?
Yeah.
What does that mean? Z1 plus C2?
Well, we have three faces, and two of them are kind of connected by a Z2 action.
Okay. But there's no like if you have a SPTs for a group, there's a notion of stacking them to get a third SPT, but for a non-invertible symmetry, there's no notion of stacking.
Yeah, because for a group, you can, if you stack, you can continue to consider the diagonal group.
Right.
Right. But for non-invertible symmetry, it do not have a diagonal. That's right.
So there's three phases, but maybe they shouldn't. First of all, I think Z1 plus Z2 is just Z2, right? So it's like not quite.
No, there are three phases.
I know.
Z1.
Yeah, topology is a bit confusing.
Yeah.
But I also shouldn't take the group structure that
No.
seriously either, right?
There's no stacking.
I mean, first of all, this group has the wrong number of elements in it, but then second of all, there is no group anyway. That's just what I mean.
Yeah. Perhaps this is not a misleading kind of notations. Z2 I just means that there are two faces. If you do Z2 transformations, you can go from one to the other. Yeah. And in the lattice, it corresponding to the one-side lattice translations.
But there's also like a full triality that can allow you to go between the three. Doesn't mean they can be stacked. Right.
Yes. So this is the examples, but we can generalize it. For example, from the D2N symmetries in 1 plus 1D, if you gauge the Z2 symmetry, it gives you the wrapped D2N symmetries. And in 2 plus 1D, gauging a Z2 zero form symmetry will generally give you a Z2 one form symmetry, and the rest. So we cannot get a 2 fusion category symmetry. And this kind of statement can be generalized to general dimensions. And we will get a D fusion category symmetries. So therefore, by knowing the symmetry patterns in the right-hand side, we can determine the SPD classifications on the left-hand side. And it kind of translates the problems of a fusion category to that of the group. Therefore, it kind of simplifies things. And let's focus on the wrap D8 and wrap D2N SPT. So by the argument, we need to find the Z2U SSB with D2N symmetries. So we just apply the same analysis to find the subgroup with order n without these U elements. If n is odd, you cannot find the diagonal group of these two. So only the first term is unbroken, which gives you that the SPT, only one SPT in this case. If n is even, so following the similar analysis, you can either have this Zn or there is a diagonal group of n and 2. So there are two cases, two unbroken symmetries. And then you can apply the group homology analysis and give you these classifications. And here, I list all the possibilities. So if n is odd, there's only one SPT. And if n equals 2 mod 4, there are two SPT. And for n equals to 0 mod 4, there are 3 different SPTs that similar to the graph D8 case. And our method can also give you concrete lattice models with these non-invertible symmetries. Because if we construct the dual SSB models with group symmetry, it's kind of easier to construct. And we also know the explicit transformations of the Cramer-Wanier. So this gives us the lattice models with wrap D8 SPT. So here I just list them all. The Z1 case corresponding to the trivial phase, and this Z2 phase corresponding to the odd SPD and even SPT. They look kind of complicated with some 5-term interactions, but you can get them from the D8 phases with Z2 SSB and together with the Cramer-Wanier transformations. And for the D8 case, if we focus on first one, the unbroken symmetry is just Z4. So the SSB is just the icing SSB. And if you do the Cramer-Wanier, it gives you the trivial phase. And for the odd SSB, the idea is the following. So there are 2 terms. So this is the Hamiltonian with D8 symmetries. And the first term shows that you can organize the spins into unit cell with 2 spins. And the first term just aligns your spins in the unit cell to the same directions. So if you go to the low energy, so the effective Hamiltonians can be described by the spins that you can look at the unit cell as a single spin. And then the second term will reduce to the interaction of sigma y. And the symmetry operators will be reduced to the identity and the product of sigma y's. Therefore, these Hamiltonians preserve the Z2 times Z2 symmetries. And by doing the Kramer-Weiners, you will get the radiate SPT models. Yeah. And the second phase is given by one-set lattice translations from the odd SSB. And I claim there are different SPTs. How to show that? Because different SPTs can have edge modes when you put them on a closed chain, like I said for the invertible case. So now, yeah.
So you have two unbroken Z2 symmetry, which are not Pauli-like operators, right? In a symmetry breaking of D8, you have two Z2 unbroken.
Yeah.
And those two symmetry operators are not like products of Pauli X operator.
Yeah.
And is there any canonical way to construct the SPT Hamiltonian between two such Z2 operators?
You mean
Lattice.
this one?
Yeah, for example, you have the Z2 eta square and the Z2 eta U.
Yeah. I see your point. So I do not have direct constructions, but we can show that if you do a lattice translations, this one and this one will have some projective representations at the interface. Yeah. This is kind of inspired from Southen's papers. They already have some constructions for rep D8, and similar things happens also here for rep D2.
Sorry, was the question how to construct a lattice SPT for Z2 times Z2 symmetry?
Well, it's not the, so this Z2 times Z2 is not the spin flip. Yeah.
If it's Pauli-like or a shift operator for your local qubit, then it's there's a canonical construction co-cycle. But for
just the cluster state, right?
Sorry.
The cluster state is
the cluster state is for the Pauli X operator. Yeah. I mean,
when in general your symmetry operator is not like a local shift like Pauli X, then it would be trickier. Yeah. For example, you have a local swap of two qubit symmetry and the local Pauli X. Those defines Z2 plus Z2 symmetry. But to write out the SPD, Here, how does the eta square act?
Eta squared.
The Z2 eta square, how is represented on your lattice?
Oh, it just eta is just the spin rotations. It's just the exponential of some Pauli Z operators.
Okay.
Yeah. Yeah, thank you for the questions. Yeah. So for example, we want to distinguish this different rep-D8 SPT. We just put it on the closed chain. On the left side is a trivial phase, on the right side is an odd phase. We want to see that at the boundaries, we will have some projective representations. So the story goes similar. We acting the operators on the ground state, because on the ground state, we have some constraints that can simplify these operators. So the operator with spin flip on the even side goes to 1, and the operator of spin flip on the outside factorized at these two boundaries for giving a sigma y at each boundary. And you can also act the non-invertible operators. And it also factorized. First, it factorized to 2 terms, and for each term, you have sigma x or sigma z located at the boundary, one of the boundaries. Therefore, we have kind of 2 copies of projective representations. At each boundaries, we have two kind of this anti-commuting relations, and therefore we have the projective representations, and we have the edge mode at the boundary as an interface, and these two are different SPT phases. And one comment is that for invertible SPT, we only have one copies of projective representations. But here, for the non-invertible SPT, we have two copies. And the constructions and analysis can be generalized to wrap D2N SVT in 1+1D. And we also study non-invertible symmetries in 2+1D, for example, in this triangular lattice. So we also do the similar things. We first consider a zero form D2N symmetries. And here, we can consider a general lattice. And on each side, the Hilbert space is C2 times Cn. So therefore, there's a spin 1/2, also a Zn spin, and which acted by the poly X sigma X or the clock and shift operator X and Z. So we can have some symmetry operators. One is a Zn spin flip symmetry operator. The other one is a Z2 operator given by the charge conjugation of the Zn and the spin flip of the Z2 product of them. You can check that they follows the D2N symmetry group structures. And what we do is similar. We gauge the non-normal Z2 subgroup, and we will get a non-invertible symmetries. To implement it directly on the lattice, we couple the theory to Z2 gauge field on the link, and we impose the Gauss law constraints to project the extended Hilbert space to the gauge invariant sectors. And our symmetry operators will be transformed accordingly. For example, we gauge the zero form symmetry, we will get a dual one form symmetry operators, which is the product of the gauge field, Z2 gauge field along the loop. And our zero form Zn symmetry will become a zero form non-invertible symmetry with a fusion algebra like the cosine fusion rules, but they are kind of discrete. So there are some discrete subsymmetry of the cosine symmetry. And actually, you can see that our constructions do not depend on the details of the lattice. So it can be generalized to arbitrary lattice and for arbitrary dimensions. You will have in the arbitrary dimensions. So this new quantum symmetry is still a product of gauge operators around the loop. And in higher dimensions, it will become a higher form symmetry operators. And in our paper, we also show some examples of non-invertible SVTs in 2+1Ds. So idea is similar. We first construct some Z2 SSB models with symmetry D8. Here, the first term tells you that it is a Z2 SSB, and the second term is try to stack some Z4 SPTs to these SSB models. So M equals to 0 and 1 corresponding to distinct Z4 SPT. And by doing primary one-year transformations, we will map these two models to different SPTs with the two rep symmetries. So I will not give you the details, but we also check that at the interface, for example, we put the M equals to 0 and 1 on the left and the right side of the lattice, and there's a red line, which is the interface. We show that the interface cannot be tributary gap, meaning that there are some anomalous edge modes. And here in the higher dimensions, the difficulty is first you need to construct some Z2 SSB in the higher dimensions. If we know the constructions, we can get the non-invertible SPTs accordingly. And the interface between distinct non-invertible SVTs will have some anomalous edge modes. Now the interface is 1+1D, so it could potentially have some gapless edge modes. And then I will go to the summary and outlook. First, we proposed a general method to study gapped faces with dual non-invertible symmetry from the information of the gap faces with original group symmetry. And we got a full classification of SVT with non-invertible symmetry that do from the D2N symmetry. And we also construct and analyze the rep D2N SVT in 1+1D and some 2 rep SVT in 2+1. And here are some outlook. First comment is that theory ahead of experiments. So in condensed matter field, in the last centuries, from the finding of quantum Hall effects, it boosts the theoretical study of topological phase of matters. And now we have more understanding in the theories. We have new generalized symmetries. We can use it to classify finer phase of matters. And this is a similar case as in the HEP-TH. We have string theories that ahead of the experiment. But in the condensed matter field, I think doing the experiment in the lab is much easier than doing experiment in the Collider physics, for example. So we have some potential to test this new phase of matters with these novel symmetries in the lab. And there's some physical kind of outlook. So the dual non-invertible symmetry by gauging a normal subgroup in a general case could be interesting. And other gapped phases like the SSB phase or topological orders with non-invertible symmetry could still be interesting. And it is interesting to study the anomalous edge mode at the interface of different SVT phases with non-invertible symmetry in 2+1D. And I just gave you 2 examples of the SVT with 2 rep symmetries. It is interesting to give a complete construction of this SVT with this symmetry. Finally, is the how to realizing these novel phases and edge moves in the laboratory. In the end, I will leave Weinberg's note. So it is possible to have a theory to have a higher degrees of symmetries that was hidden. And our physics task is to find these deeper symmetries and to find its applications. And thank you.
I have a question. So you mentioned, since you mentioned experiment, so what is the status in condensed matter experiments in identifying one example of SVT realized in the lab?
I know recently Sakura's group, they kind of proposed some models with gapped phases with rep D8 symmetries.
Oh, this is with Rydberg atoms.
Yeah, they kind of propose in that way. So,
but it has not been discovered yet.
Yeah. And also for the non-invertible duality transformation like Farmers-Wanier, like gauging Z2 can be implemented in the laboratory by doing some measurement, starting from some the phases with group symmetries or states with group symmetries. Yeah, this could be potentially another way. Yeah.
So people have already implemented this?
I think Nat in Caltech, he kind of used these methods to implement the Farmer-Wanier transformation, but not apply in this direction. Yeah.
Have you tried to start from for example D2N symmetry with the anomaly?
Yeah, that's also a good question. We only do we didn't consider anomalies, but you can probably do that. Yeah.
Because then you can like generate much more.
Yeah, that's true. Yeah, here we only kind of do very simple cases like gauging Z2 without any additional information. Yeah, please.
You mentioned you know how to implement these things as like point blank defect impurities. Do you have the formulas or?
Yeah, I think not for this case, but yeah, I mean, let's think. Yeah, for Farmers-Wanier, this Z2.
Oh yeah, I know in that case, but I was just curious if you have it in your.
I think because our symmetry operators can be obtained by the sandwiching, and the defect, I imagine it could be done similarly. You can have the D defect and the eta defect. Just
There's something that stops you at 2+1 or see.
So for the 2+1D, even the group SSB phases are difficult to construct. That's the one thing that stops. Yeah.
Questions for Weiguang?
It's sort of like understood mathematically how phases with G symmetry map onto phases with rep G symmetry once you gauge G. Or if you do any general gauging, actually,
Yeah.
it's sort of understood how phases map under gauging. Is there any like real obstruction to just once and for all solving all, constructing lattice models for all group theoretical fusion categories? For all SPTs for all group theoretical fusion categories?
That I'm not sure. Yeah, I'm also think you can study it in a different angle, like topological field theory or symmetry TFT. I think I don't know, but in this way, for my understanding, I think it is easier. But yeah, perhaps there's another way to think about this question.
I think it's probably not hard to construct them, just that if you want to make them simple construction. Right, let's thank you, Weiguang again.